Welcome to day 3 of the Scada portion of the class. Today we're going to be doing a virtual lab activity where we're going to walk through the physical devices that we've been talking about up to this point, as well as combine all of the information that we've discussed in day 1 and day 2 in order to see the full functionality of the Scada system from a physical interface to the ECC, as well as ECC back to the physical interface. The equipment that we're going to be using is an SEL 3530-4 RTAC. So this is the remote terminal unit. We are using an SEL 2411, which we've mentioned previously. We have some ABB test switches that are going to mimic some auxiliary inputs into the 2411. We're also going to be using a breaker simulator box. Since we don't have the luxury of having a physical switch in the office, we are utilizing this breaker simulator, which does the same thing. It's got the open and close coils, which turn on the, in this case, it shows 52A and 52B, but for this portion of the class, it's going to be our 89A and 89B. We're also going to be looking at the local station HMI. So this is the HMI that would be located right at the station for the operator to see alarms, as well as control points to open and close a breaker or put the DNO tag, add it or remove it, and local and remote. And then we're also going to look at what ECC screens would look like. So this is what the physical layout of our rack looks like. We have our breaker simulator down here at the bottom. And above that, you can see our test switches. And just above that is our 2411. What we're going to be looking at first is the breaker simulator. So we're going to show on the breaker simulator pushing the open and close push buttons and seeing the feedback from the 89A and 89B contacts. So this would simulate right at the switch, pushing the close button. We can see that the breaker feedback shows that the A contact is closed, and then when we trip it, we can see that the feedback is open. What we're going to look at next is the 2411 push button open and close. So we are going to, with the local on and DNO tag is off, we're going to be able to push the open button. It's going to go through the logic, and we're going to notice this 20-second delay, which is going to have a flasher to the push button 4 LED. Once that 20 seconds has elapsed, we'll see the actual control logic go to the output of the 2411 and close the switch. I'll also show you with the local off how the AND gate here allows it so that you can't close it. Turning that back on, we'll be able to actually close the switch. We'll see the 20-second delay. We'll see push button 03 blink, and then actually close the switch. We'll also look at the operation counter. So once the switch is closed, we'll notice the operation counter increment by 1. All right, so as you can see, the local is on, DNO is off. We press close. We get the 20-second timer activated to blink push button 03 LED. As you can see on the breaker simulator, we've got the 52B or 89B contact. Once the timer elapses, it will Close the breaker. So there it is, the light on the LED has enabled. We also don't have feedback from the 89B, so we have to close the test switch there, which shows that the breaker is closed. Turning off the local, we can see that if we try to open it, nothing works at the 2411. And enabling local, pressing the open button again, will again go through the 20-second timer, linking the push button 04 LED. We can see that currently the 52A or the 89A status is illuminated. And once the 20-second timer has elapsed, we'll see the 52B pick up. Again, we don't have feedback from 89B, so closing that switch will increment the operation counter and show that the switch is open. Moving on to some physical inputs of the 2411, we're going to be looking at the 43 normal maintenance switch, the loss of DC input, the loss of AC input, as well as the 89 ground switch. Starting with the normal maintenance switch, you'll see that the input is directly tied to TO3 LED. So when we close the switch on that, we should immediately see TO3 LED pick up. When we close the loss of DC test switch, we're going to hit a 20-second pickup. So the 20 seconds will count down. Once it's elapsed, we will see that on the LCD display, it'll say loss of DC, but it will also go into a TO4 LED for a motor op alarm. Same for the loss of AC. We have a 20-second pickup. Once the 20 seconds has elapsed, we'll see the LCD display show the loss of AC, as well as go into the TO4 LED for a motor op alarm. The last input we'll look at will be the ground switch. So when the ground is, the test switch is put in, it'll go directly to the LCD display point and show that the ground is enabled. All right, starting with the 43 normal maintenance switch, we put the test switch in. As we saw on the logic diagram, the LED 03 illuminates immediately, and when we take it out, it drops out. The loss of DC, again, as we saw in the logic diagram, this has a 20-second pickup timer. So once 20 seconds has elapsed, we will see the LCD screen show that it's loss of DC, as well as illuminate TLED 04, which is the motor op. So there goes the motor op. Can't see the LCD screen here, but it is on there. We'll see it in the loss of AC. Loss of AC, again, we close the test switch. We hit the 20-second pickup timer. Once the 20 seconds is over, again, we'll get a better visual of the LCD screen for this, for the alarm display, and then we'll also see the motor op alarm pick up. So there's the motor op alarm, and there's the LCD to say loss of AC. Next is the 89 ground, which again is an immediate. So we can see when we close it in, immediately on the LCD screen, we get the switch, and when we take it out, the LED screen will go away. Now that we've looked at a few examples of the logic within the 2411, we are going to move over to the DMP portion of Scada here. So we'll notice that when in 301 goes high, we can tell that we are monitoring within our DMP map directly input 301. So the second we close that switch in 301 is going to go high. Also look at the loss of DC and loss of AC. As you notice, we're not monitoring the in 304 or in 401 input. We're actually monitoring the pickup timer output, so SV10T and SV11T, which we can see SV10T and SV11T. So after the 20 seconds has elapsed, the 10T and the 11T will go high, and we'll see that within the RTAC configuration. What we'll see is the RTU tag aliases. So we'll see the 27 DC, the cabinet heater, 27 AC, the 43 normal maintenance for tag aliases. After that, we're going to look at the 43 local on. So this 43 local on comes from the push button itself. So we'll see the local on status, which is LT01 here. So we'll see the 43L go high with the latch, the set, and the reset. The next thing we'll look at as well is the position trouble. So the position trouble is the 89A and the 89B contacts. This is if the contacts both show open or closed at the same time. If they're both open or they're both closed, the switch is in a position that it shouldn't be in. It hasn't physically opened or it hasn't physically closed all the way, and we want to notify the operator that there's a position trouble of the switch. Because of the travel of the switch, it takes a while to go from open to close and close to open. So we give it a 20 second pickup before we post that there's a position trouble. Next thing we're going to look at as well is just the offline of the relay, what it looks like within the RTAC if we were to completely disconnect communications, which will send an alarm to Scada to let them know that their relay has stopped communicating and they need to either send somebody out to investigate or replace the unit, fix the unit, whatever it ends up being, replace a fiber cable that might have gotten broken, and so forth. Jumping over to the RTAC, which we saw in day 2. So we are now online with the RTAC and we can see live values. You can see that we've got some black boxes that say false and some blue boxes that say true. So that's the status feedback from the 2411 here. So what we're going to do is we're going to start putting in some physical test switches and see what it looks like. So the first one is the normal maintenance switch. When we put that in, we can see the instantaneous true for the 43 normal maintenance. And then when we take it out, it will drop to false. The next thing is the loss of DC. So again, as we saw in the logic diagram, the loss of DC has a 20-second pickup. So we put the test switch in, and right now the relay itself is going through the 20-second pickup. And once that 20-second pickup hits, we'll see the LED as well as the loss of DC go high. Same for the loss of AC. We put the loss of AC in. It goes through the 20-second time delay pickup there. Same as the loss of DC. And once that 20 seconds has timed out, we'll get the LED on the front of the 2411 as well as the alarm within the RTAC. So the next one is just a push button. So you'll see the 43L push button. Second we push it, immediately goes to true in the RTAC because there's no time delay pickup. And then when we take the 43L off, it drops low. Next one is the position trouble. So position trouble, again, is when the 89A and 89B contacts are both high or both low. This again is a 20-second pickup. So if they're both in the open or close position, 20 seconds later, it'll pick up and we get the position trouble. And then once either one goes high and low in their opposite states, it'll clear. So let's go over to the offline bit. So this is physically going back to the 2411. You'll see at the bottom, the offline bit will disconnect the network cable and the offline bit goes high. This means that the communications from the RTAC to the 2411 have been interrupted and there's no communication. So going to the controller portion of the RTAC, we can also see the offline bit is true. So once we plug that back in, communications start back up. We can see the message set count start going up and the offline bit goes false. So let's move over to the HMI. So this is the local station HMI, which the operator would see at the control house. So the HMI in this case is tied directly to the RTAC. So the DMP map that goes from the 2411 to the RTAC, it's mapped directly to those DMP points. So anytime a 2411 point goes high or low, it's immediately shown on the HMI. So we're going to go through a few examples of that. The first one being the normal maintenance mode. So when we push the test switch for normal maintenance, the 2411 communicates directly to the RTAC, and then the second that the RTAC sees that, there's a tag within the HMI that's mapped directly to this normal maintenance mode, and it'll go high, just like that. And you can see the visual feedback on the HMI screen for the operator to see that it is in maintenance mode. We're going to continue on with some of the alarms. I've sped up the time so we don't have to go through the 20 seconds, but again, first one is going to be loss of DC. So again, we've lost control DC, and logic is going to pick it up. It's going to send it to the RTAC, and we're going to see the loss of DC here on the HMI screen, showing the operator that they've lost DC. Next one's the cabinet heater loss of AC. Again, we've sped this up for time, but again, good visual indication to the operator when they come to the screen that they've lost the cabinet heater AC. Again, position trouble, as we've seen previously, when the 89B and the 89A contacts are in the same position. You know that the switch has not gone all the way through, and it's in an unknown position. Again, we can see a door open on the bottom here. So second that the door is open at the mech house, it will indicate to the operator that the physical door has been open, just in case they're leaving the station for the day. They look through here and they can see the doors open. That will allow them to go back out to the yard, close the door, lock it up, and make sure everything is secure. So we've looked at the open and close from the breaker simulator box as well as the 2411. Let's look at opening and closing the breaker from the HMI. So going back to the logic diagram, we can see the HMI open and the HMI close remote bits. These are driven directly from the HMI. So when an HMI open is pushed on the HMI screen, it will enable RBO3, and HMI close will do the same for RBO4. Let's look a little bit closer at the logic here, just so that we can get an understanding of what's going on. So the HMI open is going directly, the first thing it hits is this AND gate. So we need to make sure that the HMI is enabled. This is so that the operator can actually open and close from the HMI. If there's someone out at the switch and they don't want anyone to control it, they'll disable the HMI so that they know they have full control and the switch isn't going to operate with somebody in the control house for safety reasons. So we first need to make sure that the HMI is actually enabled. Once it goes through that AND gate, it goes into another AND gate here. We can see the first logic is local on. So HMI being a local device, we need to make sure that it is, we're enabling local on. And the next one is do not operate. You can see this not here with a circle. So we want to make sure that the do not operate is off. So it needs to be in local, and do not operate is not on. And once that, do not operate is not on. So once all of those are true, it'll go through this OR gate and then open the actual switch. And the same goes for the close. We need to make sure that HMI is enabled, local is on, and we're not, do not operate is not enabled. So let's have a look to see what that looks like on the HMI. Back onto the HMI screen, you can see that the operator has physical control of the local and remote. So putting it in local, you can see that the feedback of that button shows that the station or the switch is in local, and back into remote. The feedback to the operator goes into remote. So from here, going back to the logic being in remote, which is not local, the operator cannot open the switch. So you can see the operator press the open button and nothing happened to the physical switch. Going back to local, with the operator opening the switch, we can see the animation of the switch actually open, and the open button turn green. The LED on the left of the open button turned green. And again, if we close it, we can watch the animation show that the switch is actually closing. And to the left of the close button again, we can see that the LED there has illuminated, showing that it's closed. The operator also has control of the do not operate. So turning do not operate on, we can see the feedback. And again, back from the logic, with do not operate on, the operator is not able to open the switch. Removing do not operate then again allows the operator to open the switch. The last section we're going to look at is the communications from the RTAC to Scada. Looking at the RTAC config here in the Scada binary outs, this is the controls. We can see the mapping that's occurring. So the way that this is set up is it's saying that the 2411, when the Scada sends an opper trip, then it sends it directly to the 2411 for an open. And when the Scada sends an opper close on binary out 1, it's going to send directly to the 2411 a close command. So here is the Scada map. Again, we can see it's binary out 1. And this is the only command that they have from Scada. They can only open and close the breaker or the switch from Scada. So going back to the logic diagrams, Scada sends their open command. It's going to hit RBO1, First thing we hit is the AND gate, and we want to make sure that it's not in local. So we want to be in remote. And then that's going to send it all the way across and open the switch. And the same for SCADA close. We want to make sure that local is not on when we close it. We're also going to look at the status points or the binary endpoints from the 2411 to the RTAC to SCADA. So this is our mapping. So for the 89A contact, we can see that from the 2411, we're mapping it directly to SCADA point 001, which is the 89A DMP point, and again with the B, mapping it directly to 2. So when the RTAC receives the 89B point, it sends it directly to SCADA on binary in2. And we can confirm this by going to the SCADA map here. So we can see on binary in1 is the 89A contact, and binary 2 is the 89B contact. What we're looking at here would be the ECC screen. This is what the ECC would see at the control center. It's very similar to what the operator would see. You can see that the local and remote, there are no physical push buttons because they can't operate local and remote, as well as the DNO tag. The only buttons that they have, as we saw with the SCADA map, is the open and close. So let's look at what it would look like for feedback. So in this case, the normal maintenance test switch has been turned on. So the ECC operator gets that visual feedback of the normal maintenance switch, allowing them to see that there is an issue. You can see again, local remote, they only get the status feedback. So let's jump over to the HMI at the local station, put it in remote. Changing back to the ECC screen, you can see that they do have visual feedback that the station is remote, which allows them to open and close the breakers, the switch. So they're going to close the switch. The animation occurs. They can see that the switch is actually closed at the station. And if we were to jump back to local, we'll see that the ECC operator does not have the ability here. So this is something that automation and integration engineer would be testing. They would make sure that in local, the SCADA operator can't operate it, but in remote, they can operate it. So jumping back to remote, we can see now that the operator can open the switch, and the DNO tag, again, there's no control for the DNO tag. So the only thing that the ECC can do is see the visual feedback. So in order for the DNO tag to be added, the local HMI operator, the local operator at the HMI would have to enable it or remove it. And next, we're just going to look at a few of the alarms that we've seen previously. Again, a lot of this is sped up for time. So loss of DC comes in as it would at the station. The cabinet heater loss of AC, again, visual indication to the control center that they've lost AC. And the door open, this allows the control center to know if a door in a mech house has been left open or if it's closed, so that they can call the local person at the station to say, hey, close the door before you leave. And with that, we've wrapped up both the lab work and the SCADA segment of EET 423. A big thank you to everyone who joined me over the past 3 classes. I truly appreciate your participation and hope my presentation sparked some interest in the fascinating world of SCADA. Thank you.